Hi guys, so the last tutorial of this class, last tutorial as well as the last lecture. So now as usual in all my tutorials the way I have covered, the first we will be solving few objective type questions and then we will go on to solve few problems like here, but one thing is that for solving problems for SVM classifier, it is very difficult to get some toy problems for that, because here solving some problems means we will be needing some small problems, right? Where we can find out the optimization function, and then from the optimization function we need to compute the MMH, and if we need to do transformation also. So it is very difficult to do using pen and paper, and as such formulate such a toy example, it is really difficult. So the problems what I have kept here is just one simple toy example I have kept for classifications, but the other problems just how to use the Lagrangian multiplier, how to use the how to solve the optimization problem using the Lagrangian, that is the convex optimization problem using Lagrangian multiplier. I have just given some problems on that because that experience will also help, right? And now first coming to the objective type questions. So these are also very easy ones. So first is support vector machine is based on. So support vector machine is based on what? It is based on a supervised learning algorithm, it is based on an unsupervised learning algorithm, regression analysis, logistic analysis. So support vector machine is not based on the regression or logistic and logistic regression. It is it is a classification supervised SVM we have used for classification. So when we have used for classification, we have used our training data has the class level. So definitely when our training data is a class level, so answer to this question is the supervised learning algorithm. Fine. Then the vectors which are lying on the decision boundary, that basically gives the complexity of the SVM also. What are those vectors called? Those vectors are called training vectors, those vectors are called test vectors. What are training vectors? Training vectors are which we those vectors which we use to train our SVM, that is called training vectors. What is a test vector? Test vector, test data which we want to test, that is called a test data, test vector. And the support vector, training vector due to noise, okay, out of question. So this is the lying on the decision boundary, this we call it the support vector, and support vector also gives the complexity of the SVM as well. So support vector machine can be used for, okay, this question, support vector machine, this we have seen that we have used support vector machine for classification task, but however support vector machine can also be used for regression and also be used for ranking. So we have not seen those two. This is a bit advanced topic. If you are interested, you can just learn it by yourself. Once you have the idea, the thing is that basically in SVM also the amount of lecture I have covered in SVM, that is actually, if you consider the SVM literature, it's a huge literature. That is the for just covering SVM literature, if I try to go into the depth of SVM, go into the every nitty-gritty of SVM, it will be taking at least say 15-20 lectures, which is really not feasible. Here the objective behind is that once you know what is, once you can understand the concept, once you know what is, then you yourself can do some self-study and you yourself can learn those things. It becomes very easier. Once you know the direction, know the concept, then you can go ahead. So that's with that logic actually I have discuss the SVM. I did not go into depth of the SVM. So now similarly this SVM machine which we have used for only classification, but however it can be also used for regression analysis and ranking tasks. So answer is this. Okay, the goal of SVM is to find the optimal separating hyperplane such that. So what is the goal of SVM? Our goal of SVM is to find out the maximum margin hyperplane, isn't it? That is our goal. So what it is given? It maximizes the margin of the hyperplane. It minimizes the margin of the hyperplane. That is definitely not. It minimizes training error, maximizes test error. When we are trying to our classification, and always in any task our goal is to minimize training error, minimize test error, both the thing. We don't need more test error and less training error, or the vice versa. We need optimal of both. So this is definitely out of question, this is also definitely out of question. So it maximizes the margin of the hyperplane. That is our goal. So now here, consider the following data set. We are performing a binary classification problem, okay, using linear SVM classifier. Fine. The points are circled red that are representing support vectors. So these are the support vector. This is one support vector, this is one support vector, this is one support vector. If I remove any one red point from this data, if I remove any one red point, if I remove this, or if I remove this, or if I remove this, if I remove any one of these data, does the decision boundary will change? Yes. The equation here, the answer to this is yes, because the support vectors decide the decision boundary. It is the support vectors which decides the decision boundary. So if the support vector, if I play around with the support vector, definitely my decision boundary will also change. So does the decision boundary will change if you remove any one red point? Answer is yes. Okay. Next question is the same question. If you remove any non-red circle points, if I remove any of these points, I don't reform the support vector. If I remove any of these points, does the decision boundary will change? No, the decision boundary will not change because the decision boundary is very much dependent on the support vectors. What is true about the kernel in SVM? Kernel function maps low dimensional data to high dimensional space. This is obviously it does that, doesn't it? Kernel function, what is that? It implies the similarity in the transform space, taking the data from the input space, isn't it? So it is a similarity function. So both are correct. So only one is true, 1 is true, 2 is true, both 1 and 2 are true. This is the answer. Which is not used as a kernel function, it's support vector machine. Sigmoid kernel is used, we have seen that. Radial bias RBF kernel also used, we have seen that. The table in the last lecture I have given some list of some kernel functions where this is the polynomial kernel also we have seen where we have this p to the power p is the user defined we can use. Any nonlinear polynomial definitely it has to satisfy certain constraint and only we can say is a kernel function. So this is the answer. What is the purpose of the kernel trick? What is the purpose of it? Now you know what is the purpose of the kernel trick. Let's see what are the options given. To transform the problem from regression to classification, is it the purpose? Definitely not. To transform the data from non-linearly separable to linearly separable, yes, of course. To transform the problem from supervised to unsupervised, definitely not. None of the above, definitely not. B is the answer. Which one of the following is the correct equation for a linear separator, that is a hyperplane? All symbols bear their usual meaning. Correct equation of a linear separator. Correct equation of a linear separator, which one? Definitely. This one is, this is not a linear separator, less than equals to 0. In the hyperplane should be equals to 0, right? So this is the one. This if I take k this side then it will be equals to 0. So in a hyperplane it will be, when it lies on the hyperplane then the point will lie on the hyperplane, the value will be equal to 0. But here on the above the hyperplane we will get a positive value, below the hyperplane we will get a negative value. So this is the equation. Now some problems. As I told you, these problems are not classification problem per se. Suppose a company produced two goods X and Y. Okay, as per company's policy, total 42 goods need to be produced each month. Okay, the total production cost of the company follows a cost function. So this is the cost function of the production cost. Okay, so it produced two types of good X and Y, and this is the cost function. The owner wants to minimize the production cost. Okay, while maintaining the constraint that the total number of product in each month is X plus Y is equal to 42. Find a solution for XY using the Lagrangian multiplier method. Even if you don't have mentioned Lagrangian, we know we can very well use this Lagrangian multiplier method because this is an optimization problem where we need to minimize this subject to this constraint. So which one will be? It is a convex optimization problem or with equality constraint. This is the equality constraint. We have X plus Y is equals to 2. So equality constraint means we will have we'll find out the Lagrangian. Once we find out the Lagrangian, then Lagrangian will do the differentiation of Lagrangian with each input attributes. So in our support vector we have seen we have used the we have differentiated the Lagrangian multiplier with the different attributes. The different attributes means we have differentiated with xi's, different xi if there are n dimensional. So del of L by del of 1 x1, del of L by del of x2, x2, del of L by del of x3, likewise del of L by del of xn. Then also we have differentiated with respect to b, del of L by del of b, isn't it? That's how we have found out the different equations. And then once we found out a different expression, then we found out the values of the w and b. And of course we have also differentiated del of L with respect to the different dummy parameters, this lambda also, del of L by how many dummy parameters? If there are 2 dummy parameters, del of L by del of lambda 1, del of L by del of lambda 2. The number of dummy parameters are there, we will have to differentiate with respect to those also. So the Lagrangian, we will differentiate the Lagrangian with respect to all of the input parameters as well as all of the dummy parameters. And then we have a couple of equations, we will solve these equations to find the value, keeping in mind the constraint that we need to satisfy. So that was equality constraint problem. So here also it is a equality constraint problem. So like we have to minimize this subject to this. So how we can form the Lagrangians? This is how we can form the Lagrangian. So this is fx plus lambda of the constraint. So my constraint is this x plus y. So this I can write it in this form, isn't it? 42 minus x minus y is equals to 0. I want to equalize it to 0. So this is my what to say, constraint. Constraint is equal to 0, equality constraint. Okay. So this is here. So I will do the differentiation of L with respect to x, differentiation of L with respect to y, differentiation of L with respect to lambda. So with respect to x I got this, with respect to y I got this, with respect to lambda I got this. Then I solved this tree expression and I found this is the value for x. This is a very simple equation, so I could easily solve it, but for a bit complex equation I will have to use some numerical techniques method. So I got this x value this, y value this and lambda value this. Okay. So the company must produce 25 of the first good, and you see this satisfies the constraint also, x plus y is equals to 42, it is satisfying the constraint as well. So the company must produce 25 of the first good and 17 of the second good to minimize the cost, maintaining the constraint. Okay. Again another one problem of optimization. Solve the following optimization problem. Maximize this subject to this. Remember our convex optimization problem we used for minimizing a particular function subject to inequality constraints where our inequality constraint was less than equals to. If you can remember, our inequality constraint was less than equals to, and we are minimizing the optimization function. So if it is greater than equal to, then what we will do? We will be in our Lagrangian we will be subtracting it, right? So this maximization problem we can make it minimization. Easily we can do that. So our Lagrangian is this. I have changed it to minimization because this was maximization, and this since it was greater than, so I have used minus instead of plus. If it is less than, I would have used plus of lambda 1 into this, plus of lambda 2 into this. So this is my Lagrangian, and in the Lagrangian I have to have some KKT constraint also. Remember what what to say, convex optimization problem for inequality constraint. So I have to define the Lagrangian, and then it should satisfy certain KKT constraints. So what are the KKT constraint? KKT constraint is that del of L by del x1, del of L by del of x2, whatever I get, that those two is equals to 0, and I don't differentiate with lambda 1 and lambda 2. I don't differentiate the L with the dummy parameters for the inequality constraint. Rather I have some other constraint, KKT constraint, if you can remember KKT constraint. So what are the KKT constraint? So first I have done del of L by del of x1, del of L by del x2, these are the two KKT constraint. Now this I have just kept it to just to remind you that this is not required for inequality constraint. For equality constraint only we differentiate with the dummy parameter. So for inequality we don't differentiate this. This is not required. Then another what are the other KKT constraints? Other KKT constraints are the constraints, inequality constraints what is already there. So these are the inequality constraint. Lambda 1, lambda, all my lambda 1, lambda 2 should be greater or equals to 0. Lambda I should be greater or equals to 0. This is one KKT constraint. And then whatever is the whatever the constraint specified. Then another one is lambda I xi is equals to 0. This is one KKT constraint, lambda I xi equals to 0, and then hi equals to 0, and then this is lambda I greater equals to 0. These are the different KKT constraint, isn't it? So we have this is one KKT constraint, x1 plus x2 less than equals to 4, and my lambda 1 greater equals to 0, I can write it this way, this is equals to 0, this into this. So similarly, this x1 plus 3x2 minus 9, this is less than equals to 0, and this lambda 2 greater equals to 0, I can write as this is one KKT constraint, this is one KKT constraint, this is one KKT, this is one KKT constraint, and these are the two KKT constraint. We have the different KKT constraint. Now using this KKT constraint, we will be solving the value, finding out the value for x1 and x2, taking different combination of lambda 1 and lambda 2 value. We have two dummy parameters, that is lambda 1 and lambda 2, and it is specified that lambda I should not be greater, should be greater or equal to 0, it cannot be less than 0. So I will take different combination. What are different combination? I will take lambda 1, lambda 2, 0, lambda 1 greater than 0, lambda 2 equals to 0, lambda 1 is equals to 0, lambda 2 greater than 0, lambda 1 greater than 0, lambda 2 greater than 0. For all these combinations, there will be 4 such combination, 4 such combination. I'll be using just 4 combination and will try to find out the values. So basically, these are my obtained constraints. Whatever I have in the last slide, I have written it here. Now with different case, this already we have solved it. You can just go through different steps. I don't need to explain this. We will take for each case, we will take separately. First case is lambda 1, lambda 2 equals to 0. If lambda 1 and lambda 2 equals to 0, what does this expression become? This expression become minus 2 of x1 minus 4 is equals to 0. This expression become minus 2 of x square minus 4 is equals to 0. Okay, and lambda 1 is equals to 0, lambda 2 is equals to 0, then what happens? If lambda 1 is equals to 0, lambda 2 is equals to 0, then we will be using this x1 plus x2, this and this. Suppose lambda 1 is greater than 0. If lambda 1 is greater than 0, then I can write x1 plus x2 minus 4 is equals to 0. Then I can use this also as an equation. Again, if lambda 2 is greater than 0, then this will be equals to 0, x1 plus 3x2 minus 9 is equals to 0. So that way I will be having all the equation, then I can find out all the solutions, and once finding out, for there are total 4 cases as I told you. For the 4 cases you will be finding different solution. Now from among this solution you will have to find out which is the feasible solution. If there are more than one feasible, if there is one feasible solution, then that is the only solution. If there is more than one feasible solution, then among the feasible solution you will have to find out which is the optimized solution. Okay, and accordingly that is the solution. So you can just go through these steps. In fact, please don't go through these steps, you do it yourself, and once you get the answer, then you try to match it with this. Okay, so this is how this are I am not going to all through the steps, you can do it on its own. So we got the, finally we got the solution x1 and x2 is equals to 2, and it satisfies the constraint also. What was the constraint? X plus x2 greater equals to 4, that is, it is satisfying the constraint as well. Now here, okay, here's one just toy example of a classification problem. As I told you, this is a toy exercise. This is not at all a realistic, because for classification, for developing an SVM, we need more and more observation. We need more and more training data with a level, class level. Then only we can come up with a proper maximum margin hyperplane. So it is just a toy example, just to see, just to utilize the concept. So suppose there are 3 points. So what are my points? This is one point. This is the another point. This is my third point. That means it is that each point is a 2-dimensional. It is in a 2-dimensional space. Here P1 and P2 are the negative class. This 2 belongs to negative class, and P3 of positive class. 2 class, negative and positive. Compute the decision boundary as learned by the SVM classifier. Okay. So first, what will I do? So I'll consider this is my decision boundary. Wx plus b is equals to 0. Okay, so since it's in 2-dimensional, so I'll be having 2 parameter w1 and w2. So w1 x1 plus w2 x2 plus b is equals to 0. So we need to compute the values w1, w2 and b. Find this SVM learning problem is given by minimize. We'll need to minimize this, subject to this for all I. Fine. So first we'll define the Lagrangian. That's so my Lagrangian is this. Minimize this. So it is greater, then since my convex optimization problem, it is less than equals to 0. Since I have greater equal to 0, so I will be using minus. So this is how I have defined my Lagrangian. Okay, so I have defined my Lagrangian. Now I will have to find out a different KKT constraint. Okay, so these are the data points I have given here in the figure, x1, x2, x3. These are the different data points, and these are the class level, which is already given class level, and these are the lambda value, lambda 1, lambda 2, lambda 3. We will have to find out these 3 values. Now, so now the KKT constraint, this is one KKT constraint, del L by del W. Okay, so then this already we know lambda yi should be equals to 0. So in our case, we n is equals to 3. So we have to find out what is W. W is this, we know this is the W, this is the formula for W. Okay, so putting this yi minus and yi will take value either minus or plus. Then similarly we found out the values for W, and this is another one expression, lambda iwi is equals to 0 means lambda greater equals to 0. So lambda greater equals to 0 minus means this is our lambda, this is equals to 0. So we will get this. So these are the 2 equations. Simple putting it in the equation and trying to solve it, that's all. Now basically, if a dual problem is maximizing this, isn't it, subject to this greater equals to 0. Now we'll put all this in this dual problem. Then we find L is equals to this. Okay, just simply putting this here, lambda yi, lambda j, yj, xj, xj, and whatever data we have, just putting the data in simple dot product. Excuse me, if you do it, you can do the dot product and see you will get this, and simplifications. And using this equation 1, we have this lambda 1 plus lambda 2 is equals to x3 or lambda 3. Using this, we will get, this is my Lagrangian. So now I found the constraint lambda L by differentiation of L by del of lambda 1 by del of lambda 2. We found this different values. So solving, we got the lambda value. So lambda 1 we got 0, lambda 2 1 by 8, and lambda 2 is equals to lambda 3, both is 1 by 8. So I got the value lambda 1, lambda 2 and lambda 3. If any values, if the lambda value is 0, that means that is not a support vector. So my first point is not a support vector, second and third point is my support vector. So here this is not a support vector because lambda 1 value is 0. For value is 0 means it does not lie in the parallel line, isn't it? So since it is 0, so it is not a support vector. These two are the support vector, but actually this is a bit trivial. See here, this is okay, let's come to that later. So now here we got this support vector lambda 1, lambda 2, lambda 3 value we got. Once we know this, then from here we can find out the W values as well. We know lambda 1, lambda 2, lambda 3 values. We can put it here and we can find out the W values. So we got W1, W2. So we need to find out W1, W2, 2 values. We will put it here and we found out the values. Once we found out the W values, we can find out the B values also. Once we find out the lambda values, W value, B value, so we can find out the equation of the hyperplane. Now my equation of the hyperplane turns out to be x2 is equals to 0. Very trivial example. Just this example is to show, just to practice whatever you have just learned. Okay, very simple example. Now here, this x2 is equals to 0 means my hyperplane is, this is my hyperplane, and this are my this point and this point I got support vector. See, if this is my hyperplane, this point I got, this is at a distance of 2, I got a this is my support vector, this is a distance of 2, I got a support vector. Since this is the x-axis, which is my hyperplane, and that means distance of 2, these are the 2 parallel lines. So these are my distant boundaries, isn't it? Now since again this surprisingly this I got as a support vector, and this point, if this point also lies in this but this I did not get as a support vector. Why so? This is a bit contrary what we have learned, isn't it? Because if this is a support vector, definitely this also should be a support vector. But actually, considering the case that this is just we are working with 3 datas, in considering these 3 datas, this if considering this as a support data is sufficient, it is actually, it makes it sufficient for this data. If I just consider this as a support vector, this is no longer, it needs to be considered as a support vector. In fact, when we see that such a case, whenever the line is parallel to the x-axis, the hyperplane is parallel, hyperplane is on the x-axis or hyperplane is on the y-axis, so then what happens? The decision boundary is just parallel to these two lines. So in that case, there may be many data which falls on the line parallel to that, but all those data is not necessary to be considered as a support vectors. Just considering few of those as a support vectors will will help us in solving the problem, because the main reason behind is that, so it is very first of all, the reason behind is that since we are working in a very small example, very small, and working in a small data, we will definitely not get a proper SVM. So the more the data we train, the more the better SVM we get. So once we get a better SVMs, then like which will be in the support vector, which is not in the support vector, then it is easier to find out. Now it is very toy examples, it makes no sense, just to find see how it works. Basically that's why we have kept this example. Okay, so now another one. Consider following two-dimensional data point for a binary classification problem. A nonlinear transformation is used to transform the input vector. Okay, we are using this transform to infer to a transform space. This is the transform space. Okay, so what is my transform function? Phi of x1 x2 is this function, and phi 2 of x1 x2 is this function. This is how we are transforming. Okay, this whole thing we are transforming to phi of x1 x2 to a different dimensional, and this whole thing we are transforming using phi 2 x2 to a different function. Transform the data to the transform space. Is there any specific observation? Okay, so this is my original data. Okay, x1 x2, suppose this original data is given and the class level are also given. Okay, the original data is given and the class level is given. Now from this original data I tried finding out my z values, z1 and z2. What is my z1? This is z1 and this is z2. I tried finding my z1 and z2 value. Now I will try to these are also two attributes, these are also two, this is also two dimensional, this is also two dimensional. I tried plotting this data. See, when I plotted this data, so these are my datas. This data, when I tried plotting this data, if you see, you will get this sort of, there is, from this figure we can see, they are not linearly separable, isn't it? Now once I have transformed it, so these are my values now. In my transform space, you see it is very much linearly separable. These are the data, usually this are the rectangle. Now here in the transform space, all into comes to one side, all the square comes to the other side. It has become very much linearly separable. So we can see that the data points in the original input space on the left is not linearly separable, but when the data points are projected from input space to the transform space, they become linearly separable. Okay. So with this, I end this lecture. I hope you have enjoyed this course. So with that, I'd like to tell thank you to all of you and then conclude this course. Thank you.